chi-squared so that you feel comfortable kind of going over them. I might make some abbreviations and go a little quickly, but hopefully I hit the most important parts each of the problems. I hope this helps. Make sure you check your work, that way you feel comfortable for the quiz. So I'm going to start with question 2 because we kind of did question 1. So using binoculars, volunteers observed feeding habits of a random sample of 320 deer shown below. Use chi-squared test to test the hypothesis that the natural distribution of plants fits the deer feeding pattern. So here are areas A, B, C, D, and E. So we checked 5 areas for deer. Plant composition, observed feeding area. So we're essentially trying to figure out if it matches what we would expect. So what we are going to do is we know that the total population of deer here is 320. And so these are the observed numbers, right? We observed 102 deer in A, 125 deer in B, 43, 27, and 23 respectively. Those were our observed numbers. Now we're trying to compare that to the plant composition in the area, and therefore we need to convert these percentages into a number. Again, we use percentages because we couldn't guarantee that we were going to collect 320 deer. What if we had collected 100 or 1,000 or 422? So you want to use percentages so that then you can find the number when you need to. So essentially what you do here is you do 320 times the frequency, or the percent. It's the same thing. We just convert the percent to decimal, and you just multiply 320 by the expected frequency of plant composition. So it should look like that. And the numbers that it gives you are going to be 102.4 for area A, 123.84 for area B, 38.4 for area C, 29.76 for D, and 25.6 for E. Now you can fill out the rest of the chart, but we know that I don't like the chart much, so I like to do the old school way. And so if we remember what chi-squared is, it's the summation, all right, of observed minus expected squared over expected for our different locations. So I have location A, B, C, D, and E, and then I'm going to add all those up because, again, it's a summation. So what I'm going to do is for each discrete outcome, A, B, C, D, E, I do the observed, 102, minus the expected, squared over the expected, just like that. And then I'm going to do an add sign, and I'm going to do that all the way through here. Observed minus expected, squared over expected. Again, the reason why we end up squaring them is so that you don't have negative numbers. And so if you set it up like that, a couple of things to think about. If you do this in the calculator, if you do it all in one fell swoop, just do be careful to make sure your parentheses are in the right order, so it essentially does the mathematical analysis in the proper order. Usually where people make a mistake here is in typing it into the calculator. So the numbers that I get, 0.01, 0.55, 0.25. If yours varies slightly, it's probably because of a difference in rounding. What those add up to is a chi, I don't know why I use the average, a chi-squared of, I don't know why I keep doing that, of 1.07. So then the next factor, if I go to my p-value, I have to figure out my degrees of freedom. And my degrees of freedom are n minus 1, which for this case is 5 minus 1, or degrees of freedom of 4. So if I go to my chart, p-value of 0.05, I know that 1.07 is, good gracious, is less than 9.49. And if my number is less, then I accept the null. And what does that mean in this particular case? It essentially means that the plant composition and deer meet expectations. So you would expect to find that many deer in that particular area And the numbers, like the variation in numbers, is just due to chance, right? Because they're not exactly the same, right? 43 and 38.4, for example, right here, they're not exactly the same, but this is saying mathematically they're close enough. And if you look, you have a 107 compared to a 9.49, so significantly close enough to accepting the fact that that the feet that observed is what we would have expected. Okay, because again, if that number had been really close, like 9.47, we would still accept the null, but we would have kind of a different opinion about it. We might say, you know, it was very close. We would like to do another sampling, because again, this is just a math principle that we are applying. Okay, let's move on to this particular problem. And I forgot that this particular problem was in here when I first assigned it. So it is a bit of genetics. It's actually a really simple problem once you get past the genetics component, but I'll talk it through because I know that not everybody got genetics. So hopefully you can see the pattern here. It says in peas, yellow seeds, which we're going to denote as big A, are dominant over green seeds, which we're going to denote as little a. In a cross between both heterozygous in plants both heterozygous, meaning big A, little a, big A, little a, that's the cross. For seed color, you observe the following. So these are our observed numbers here. And so what we're saying, I did the cross, you have a big A, little a parent, a big A, little a parent. So this is the outcome that you would expect. You would expect 75% of the population to be either big A, or big A, little a. And remember when we talk about dominant, if you have a big A, you express that. So yellow, okay, apparently these things turn into arrows. So yellow, we would expect 75% of the population to be yellow, and then 25% of the population will be little a, if you see that right here. So we would expect this to be 25% of the population. So what I can do here is I can make like a little chart. I can say yellow, observed 440, expected, I'm actually going to do 2 expected, and green, observed, was 1624. Now expected, how do I figure that out? Well, I have to figure out the total. So I have to add up the total, and I say, all right, the total number of plants that I counted was, so total plants, 6,024. And so I know my percentages here for expected, and I just apply that based on the total. So my expected would be 6,024 times 0.75 for yellow and 6,024 times 0.25 for green. And those numbers turn out to be 4,518 and 1,506. So those are my expected values for the given plants. So if I do my chi-squared, I have yellow and I have green. My observed for yellow was 4,400 minus my expected 45,118 over 45,118 plus my expected, or my observed for green was 1624 minus my expected 1506 squared over 1506. This gives me a number of 3.08, and this gives me a number of 9.25 for a total of 12.3. So now I have to sit here and say, all right, well, what are my degrees of freedom? Again, n minus 1, 2 minus 1, my degrees of freedom are 1. I come over here and I see that I'm comparing it to 3.84. And I know that 12.3 is significantly greater than 3.84, so I must reject my null hypothesis. What does that mean in this particular case? It means that the number of green and yellow are not expected, and that therefore something must be going on that is skewing the data, it looks like, toward the green plants. So that's the second, or the third problem. And finally, the fourth problem here. All right. The fourth problem, the fish and game department stocked Lake Lulu with fish in the following proportions: 30% catfish, 15% bass. I'll write this down. So 30% catfish, 15% bass, 40% bluegill, 15% pike. 5 years later, they sampled 500 fish, so total of 500 fish in the lake to see if the distribution had changed, as shown below. Use the chi-square to determine if there had been a change. So they sampled 500. That's these observed numbers right here. So these are our observed. So we can say, if you want to do the chart, you can. If not, if you can hold on to it, not a problem. And then how do I find the expected? Well, I say 500 times 0.3, 500 times 0.15, 500 times 0.4, 500 times 0.15. So the numbers I get for the expected, for catfish, it's going to be 150. For bass, it's going to be 75. For bluegill, 200. And 75 for pike. So now I'm going to put this into my equation. So we'll go catfish, bass, bluegill, pike. All right, my observed 120 minus 150 squared over 150 plus my observed 85 minus my expected 75 squared over 75. 220 minus 200 squared over 200. And 75 observed, 75 expected, squared over 75. So we know that this particular unit will cancel out and be plus 0. All right, we go back to our numbers here. This particular one is 6 plus 1.3 plus 2, which gives us a total of 9.3. Now I go to my degrees of freedom. I say degrees of freedom is n minus 1. There are 4 options. Minus 1, my degrees of freedom is 3. So I'm comparing to 7.82. And so here I'm going to say, okay, my chi-squared value is greater. I don't know why I'm doing that. My chi-squared value is greater. It's not outrageous. I don't know what I did here. Sorry. This number, my chi-squared, is 9.3. 9.3 is greater than 7.82. Oh, the 7s were getting me. So what that means is I'm going to reject the null. But on this one, I want you to look. Do you see how these two numbers are decently close? So if you were doing a scientific analysis, you would say, yes, we're rejecting the null. So there is very much a possibility that something is up. But you also might say, I think I'd like another sample. I'd like to test this again just to see if I get that same result. Because again, the closer it is to that p-value, sort of the closer it is to being within that 95%, which we consider chance. So those are the chi-squared problems. I hope this made sense. I hope this helped. Let me know. Just send me an email if you have any questions.